Hello and welcome. In this video we're going to take a look at inverse functions. Now this video is more or less just a segue really, because in the last couple of videos we looked at trigonometric functions, exponential functions, and what we want to do is get into logarithmic functions and inverse trigonometric functions in the next couple of videos. But this video sits somewhere in between them, just explaining about what an inverse function is, so you have an understanding about why we need logarithms and inverse trig functions. I'll try to keep this fairly brief and just tell you a little bit about what an inverse function is. But to get there, we need to know a definition about what a one-to-one function is. Now, a one-to-one function is some function where if we pick any a and b in the domain of that function, if a and b are not the same value, then f of a and f of b are also not the same value. It has this property where if a and b are chosen along the x-axis here, somewhere in the domain, and we know where f of a is, and that's some point up here. Let's say that's your f of a. And we know what b is. F of b is somewhere down here, let's say. Then at no point can those two have the same y-coordinate. F of a can't equal f of b. So the function can't actually cross a horizontal line. So you can kind of imagine like a little horizontal line here. At no point in time can this function ever use that y-coordinate again. And so a function that is one-to-one passes a horizontal line test. If any horizontal line passes through the function, then it can only pass through the function once. And that horizontal line test is a great way to look at a function and see that yes, this is a one-to-one function. So trying to draw a graph that never crosses a horizontal line twice makes it a little bit challenging. I can be decreasing, something like that. Now I can't start increasing again. If I start increasing again, take a look for another horizontal line here, and you see, oh, there's a horizontal line and I've crossed it twice. That's not allowed. So that can't be a one-to-one function. A one-to-one function is either decreasing or increasing, strictly just one or the other. You can't be having combinations of increasing and decreasing. So, for instance, x squared, the parabola that everybody knows well, is not one-to-one. And that's a pretty easy example of a one-to-one function. We have an example where f of 2 would be equal to 4, but f of negative 2 is equal to 4. Now, the thing about squares, if you try to imagine what you need to do to undo the operation of squaring something, that would be the square root operation. But it doesn't end up always giving you the same result. So for instance, if I take negative 2 and I square it and I square root it, first operation is squaring, that leaves me with 4, and then square rooting 4 unfortunately gives me back 2. So the operations of square rooting and squaring don't always cancel each other out. So what is an inverse? Well, an inverse is going to do the opposite operation of a function, but only one-to-one functions have inverse functions. And that gives us an idea of what an inverse function is. Now that we know that one-to-one functions have inverses, we can look at the definition here. If f is a one-to-one function, and let's say it has domain A and range B, then the inverse of f we denote with f to the negative 1, and that would have domain B and range A. It's the opposite direction. It takes whatever the result was from our function and gives us back our initial value. So in this diagram here, we've got the domain as being a set of numbers in blue, which is A, and if you choose a value from the domain x, and you plug it into the function f, let's say you get a value y. Now if you take y and you plug that value into the inverse function, it will give you the result x. So it completely undoes the result of applying the original function. So this is the real definition over here on the right. The inverse function is defined through some sort of equivalence relationship. F of x equals y is equivalent to the inverse of y being equal to x. For instance, if you just had a table of values and you were to pick a value of x in the domain of f and apply the function f of x to it, then we'd get a few points on our graph. So let's say when I plug 3 into my function, I get a point in the set b, which would be 2. And let's say I plug a number 5 into my function, and I get the result 6. And if I plug in the value 6 that's in the domain of f, let's say I get the result 9. Now, if I were to choose those values and plug them into the function, I should get the exact opposite. So here's my function. Typically, we still write f of x equal f to the minus 1 of x. That's typically what we write, is we let the variable be x. But this time, I'm going to be choosing values from the set b. Now, because I know that when I plug 3 into f, I get 2, that means if I choose 2, which is in the domain of the inverse, I should get the result 3. And if I plug 6 into the inverse function, I should get 5. And if I plug 9 into the inverse function, I should get 6. And the ordered pairs are in the reverse order. And that actually makes graphing inverse functions very easy. Every point here, if I had, let's say, x and y, or better yet, why don't we say, if I have a point a, b, then on the inverse function, I will have b comma a. That's going to help us when we're trying to graph things. And that means, well, what happens when you reverse an ordered pair? What is that going to look like when you try to graph things? If I have, let's say, a here and b up here, this would be the point a comma b. If I reverse the order, well, you can see b kind of looks like 3 here. I'm going to go 3 units over, so somewhere around here. That would be b along the x-axis, and here would be a along the y-axis, and this would be the coordinates b comma a. It has this nice result that actually, if you were to take a 45-degree line, now if you've been watching some trigonometric videos, you know that we're actually going to call that pi over 4 usually. In radians, pi over 4. There's our 45-degree line, and you can see that this is actually a reflection over that 45-degree line. But being a linear function, you can take a look at the slope of that diagonal line. It has a slope of 1. And you can look at the y-intercept of that diagonal line. It has a y-intercept of 0. So this line has the equation y equals x. So a property of inverse functions is that they are reflections over the line y equals x. All right, now we're going to dive into the inverse of exponential functions, which gives rise to logarithmic functions. And we're going to take a look at the inverse of trigonometric functions. But how about just a basic algebraic operation? Let's see if we can take the inverse of that. And we know that we can't do the inverse of x squared, so I'm going to use a function that has x cubed. And x cubed is always increasing except for 1 point, and that would actually be a one-to-one function. If you graph x cubed, then you can see it passes this horizontal line test. Here is a function that involves x cubed. F of x equals 2x cubed minus 2. And here are some steps that you can follow in order to find the inverse of some algebraic function like this. Well, first of all, let's rewrite that so that we have the y-coordinate equals 2x cubed minus 2. And once you've got this listed as the y-coordinate equals 2 times the x-coordinate cubed minus 2, remember that when we're looking for the inverse, the x and y coordinates are going to swap. So let's do that right now. Let's set x equal to 2y cubed minus 2. Now it's your job to try to solve that for y, which is only a couple steps long. And once you get to the step where you have y cubed by itself, now you're going to have to get rid of that cube. Now luckily, the cubed root of a cubed is simply equal to a. They cancel each other out. That property unfortunately doesn't work when you use the square root of a squared. That's actually equal to the absolute value of a. We won't be able to get a inverse properly of a quadratic, but we can look for the inverse of a cubic in this case. So let's cube root both sides and end up with y equals the cube root of x plus 2 over 2. And once you've done that, let's put this back into function notation. In this case, we can write it as inverse function. And there you have it. There's the inverse of our function f. It's every operation, but in the reverse order. And the two graphs, if you were to graph both functions, would be reflections over the line y equals x. Now with that, that means that we can take a look at logarithms as being inverses of exponential functions next, and then we can start taking a look at inverse trigonometric videos. So take a look for those coming up soon, and I'll see you in those videos.